Welcome, video example 4, Unit 3, Chemistry 1B. In this case, we're going to use the Nernst equation. So we're asked to calculate the cell potential for a galvanic cell employing the following half reactions and given specific concentrations. So here are the half reactions and here are the concentrations. Okay, so how are we going to do this? So first of all, we know that the ion, if we looked at the two equations, the iron is the more positive, so it's going to be reduced, and the cobalt is the more negative, so it's going to be oxidized. Okay, so when we do the reaction, or to put together the reaction for the final reaction, we see that we have to balance the electrons in order for the electrons to cancel. So we write the reduction reaction over here, and we multiply that reduction reaction by 2 so that the electrons balance. And then the cobalt reaction is over here, and that you can leave it as is, and we get the net reaction. Okay, then we can then see that the total number of moles, N, is equal to 2. Okay, so the electrons transferred is 2, and we can use the Nernst equation, which is this equation here. Remember that it's the Nernst equation is for the cell at non-standard conditions. So we have E standard cell, okay, minus R T N F ln Q. Okay. So that's where the equation comes from. It's one of the many forms of the Nernst equation. Okay, you can abbreviate it depending and rework it. But we'll use it in this form for now because we know what N is. Okay, we can work out Q. All right, we've got some concentrations, and for the equation, we see that we've got the iron 2 plus squared multiplied by the concentration of cobalt divided by the iron 3 plus squared. Okay, so that comes from the equation that we had on the previous slide. Okay, so have a look. Actually, it's on this slide as well. You can see we've got products. Remember that the reaction quotient is the concentration of the products over the reactants. So you can see we've got Fe2 plus and has to be squared because of this coefficient, multiplied by the cobalt concentration from here, and then the cobalt is a solid here, so we don't need to include it in the reaction quotient determination, and then the Fe3 plus we need to square because we have a coefficient of 2. All right, we can calculate the E cell from the information that we were given. Okay, so we can plug the values in, and we get an E cell value, standard value, okay? And then we can calculate the non-standard E cell by plugging in all the values that we have, making sure that we take care of all the units correctly. Okay, so plug in the values for R, T, N, and the concentrations. So we have, this is the E cell standard, the gas constant, the temperature, the number of electrons, the Faraday constant, and then here are the individual concentrations in the reaction quotient that we set up. We do a final calculation and solve everything, and we see that the E cell should not be a standard value at all. That is incorrect. So the E cell, this is the E cell standard value here. And we get a final E cell value at non-standard conditions of 0.98 volts. And you can see obviously this is different from the standard electrode potential simply because the concentrations are different.